Hello everyone, welcome to channel Statistica. So in this lecture video, we'll go through with the topic of linear dependence and independence. Linear dependence and independence. We have a vector space V over which, over the field F. And from this vector space V, I have the set of vectors. Let's say any V vector. I have the set of vectors say V, and I want to check whether this set of vectors be linearly dependent or linearly independent. For checking this, the linear dependent and linearly independent set, we have to first know that what are linear dependence and what are linear independence. When did we say that the set of vectors is linearly dependent, and when did we say that the set of vectors is linearly independent? Okay, so I have the vector space V over the field K, and the set of vectors from V, let's say u1, u2 to un. This is the set of vectors from the vector space V are said to be linearly dependent if there exist scalars. If there exist scalars a1, a2 to am from the field K, where the set of these scalars are not all zero. This is the main required condition for the linear dependency, that this set of scalars are not all zero, such that the linear combination of these scalars with the vectors a1 u1 plus a2 u2 to am um is equals to 0. Then ui's, these set of vectors, are linearly dependent. Okay, what did I say? Therefore, the set of vector ui's to be linearly dependent, there exists the set of scalars a1, a2 to am, which are belonging to the field K, where the set of vectors, the set of scalars a1, a2 to am, not all ai's, these all ai's are not all zero. Some of ai's can be zero, but there should be some ai's which are not all zero, which are not zero. Okay, then such that the linear combination of these ai's with the ui's vector is equals to 0. Okay, this is the required condition for the linear dependence, that the AIs AI should not all zero. Okay, and for linear independence, the this set U1 to UM is said to be linearly independent when, if and only if, when the equation, let's say this is the equation, we are considering this equation again, when the set of all ai's are equals to 0, which is a1 equals to a2 equals to a3 equals to whatever am, this set of ai's are all equals to 0. When the set of all ai's are equals to 0, then we say that the vectors are linearly independent. Okay, so this is a very simple measure to check whether the set of vectors is linearly dependent or independent. Where we get the when we get the solution of when we get the non-zero solution. When we get the non-zero solution, the vectors are linearly dependent, and when we because that means ai's are not equals to 0. This is when we get the linearly dependent solution. Because why are we saying that these are linearly dependent here? Because if ai's are not equals to 0, then there exists their inverse, A inverse. If ai's are not equals to 0, then their inverse would also be exist. Okay, and when the value of these scalars ai are all the ai's are 0, then we say that the set of vectors u1 to um is linearly independent. Okay, this is the basic requirement or basic check. How do we check the linear dependence and linearly independence vectors? Okay, so if I am saying that here the set of vectors u1, u2 to um of the vectors in V is linearly dependent or linearly independent, depends on these vectors, whether these vectors are linearly dependent or linearly independent. Okay, now there are some results. on the basis of linear dependence and linear independence. Let's read them. Before that, let's just consider an example first. Okay, if I give you a set of vectors, let's say x1, which is 1, -1 and 0, 0, 0, and another x2, which is equals to 1, 0, -1, 0, 0, 0, and x3, which is 1, 0, 0, -1 to 0, to xn minus 1, which is equals to 1, 0, 0, 0, -1, and xn, which is equals to n minus 1, minus 1, -1 to -1. Now I want to check whether this set of vectors are linearly dependent or linearly independent. From this, we can easily see that the set of vectors x1 to xn, this set of vector is linearly dependent. How? As we can see that xn can be written in their linear combination, like xn equals to x1 plus x2 plus xn minus 1. By adding these vectors, we can get our xn vector. So we are getting a set of combination of vector xn that can be represented in their linear combination. That's why it is linearly dependent. But if I'm talking about the set of vector x1, x2 to xn minus 1, this set of vector is the is that set where no vector can be written in any of their linear combination. So this set of vector is linearly independent. How I can also show this it like this, that I have to show that whether this is linearly independent or not. So let's say that in their linear combination, okay, we are considering alpha i's which belonging to their the set of scalars. Okay, so we can write in their linear combination as alpha 1 x1 plus alpha 2 x2 to alpha n minus 1 xn minus 1 equals to 0. Okay, now if I'll compute it, what did I get? Like just putting the values of alpha 1 with the set of with the vector which is 1, -1, 0, 0, 0, plus alpha 2, 1, 0, -1, 0, 0, 0, plus alpha n minus 1, which is 1, 0, 0 to 0 minus 1 equals to 0. Okay, I got from the first that alpha 1, I'll have to just form the equations from here. That alpha 1, alpha 2 to alpha 3 plus alpha n minus 1 is equals to 0. And other equations I got like minus of alpha 1 equals to 0, minus of alpha 2 equals to 0, to minus of alpha n minus 1 equals to 0, which are that all the values of alpha i's are equals to 0, and it is also satisfying this equation. So this set of vectors is linearly independent. And you can also see that I have this set of vectors x1 to xn minus 1, which I have proved that this set of vectors is linearly independent, and there is one vector xn which can be written in their linear combination. In their linear combination, then the whole set x1, x2 to xn is linearly dependent. Okay, I think you got it from here. Okay, so let's see some important results of these linear dependence and linear independence. There are some results. Okay, so let's say there are some theorems, like if set of vectors, I have a set of vectors u1, u2 to un over the vector, we are all taking the vector, this set of vectors from the vector space over the field K. So if I forget, just consider it done, that we are taking the set of vectors from the vector space V over the field K. Okay, so if this set of vectors be linearly dependent, okay, if this set of vectors be linearly dependent, what does it mean? That it means that this from this set, then at least one of the vectors of the set can be expressed as linear combination of the remaining others. Okay, that means that at least one of the vectors, let's say ui, can be represented in their linear combination. Okay, can be represented in their linear combination. That's what we mean about the linear dependence. Okay, so it can also be said like this, that if one of the vectors of the set, if one of the vectors of set be a linear combination of the remaining others. Let's write it down. If one of the vectors of set be a linear combination of remaining others, then the whole set, then the set is linearly dependent. That's what we do in the previous example. We have the set of x1 to xn minus 1, which is linearly independent. But there is one vector h xn which can be written in their linear combination. Then the whole set x1 to xn became linearly dependent. Okay. So what did we get from here? Here is the important result, that what we have done in the previous example is an important result, which can be said in two ways. That if I have the set of vectors which is linear dependent, then there is at least one of the vectors from this set which can be represented in the linear combination of the remaining vectors. And if I say that the one of the vectors in the linear combinations is written in the from sorry if one of the vectors of a set be a linear combination of the remaining others, then the set is linearly dependent. Okay, let's do it like this. How do we say that this is linearly dependent? Because let's say I have the vector ui which can be represented in the remaining of the vectors in their linear combination. Let's say alpha 1 u1 2 alpha 2 u2 2 alpha j minus 1 u j minus 1 plus alpha j plus 1 u j plus 1 to alpha m u n. Here what I have done, I am it is j. I am writing the vector uj in the linear combinations of the remaining vectors. In the remaining vectors, these are the remaining vectors u1, u2 to uj minus 1, and except uj, the j vector, j plus 1 to un. These are the remaining vectors, and I have represented uj in their linear combination. Okay, then this set of vectors u1, u2 to um is linearly dependent. How? Let's see this. If I subtract uj from this equation, if I subtract uj from this equation, what did I get? I get u0 equals to alpha 1 u1 plus alpha 2 u2 to alpha j minus 1 uj minus 1 plus minus 1 of uj plus alpha j plus 1 uj plus 1 to alpha m um. Okay, so for the linear combination, all alpha is equals to 0. All alpha is equals to 0. So if I give all alpha is the value 0, then it becomes 0 u1 plus 0 u2 to 0 uj minus 1 plus minus 1 of uj plus 0 uj plus 1 to 0 um. This is when I am considering that this set of vector is, let's say this set of vector is linearly independent. So for linearly independent, the set of scalars has to be 0. All the set of vectors, all the set of scalars has to be 0. So I am considering that if all alpha is equals to 0, then I have given all the alpha is, put it all the alpha is are 0. Then from this I say I got that here the alpha j's value is equals to minus 1, which is not equals to 0, which is not equals to 0. Okay, alpha j equals to minus 1. So the value of alpha j coefficient is non-zero. I got here the non-zero coefficient. From this I consider that the set of vectors here is linearly dependent. Okay, the set of vector here is linearly dependent. Okay, now if I say that from this set of vectors u1 to um, let's say if I say from this set of vectors I have a vector, let's say ui, any vector from this set which is 0, any vector from this set is 0, then this set of vectors must be linearly dependent. Then this set of vectors must be linearly dependent. How? Let's see it like this. Because if I represent it in the linear combination, that's what we do in the linear dependence. That if I represent it like this, how do we represent in the linear combination, which is a1 u1, a2 u2, to an un. That's what has to be equals to 0, where all ai's are not all 0, or ai's are not all 0. Okay, that's what we have studied in the definition of the linear dependence. So if I'm saying that one of the vectors from this set is equals to 0. Okay, and now I am putting all of this value of the scalars are 0. Okay, all of the value of the scalars are 0 except this thing, that this can be linearly independent, because the sum of all this set became 0. But there is one condition, that 1 dot u1 0 dot u2 plus am is equals to 0. But here we have to know that the set of u1, let's say it is u1, which is equals to 0, that's why the whole set becomes equals to 0. But the coefficient of u1 is not equals to 0, okay. So what did we get from here? We get from here that I have a vector u1 which is equals to 0. Okay, so what does it mean? That I can put any value of the scalar, any value of the scalar, alpha 1 u1, let's say alpha 1 u1, I can put here any value of the scalar 1, 2 or anything. Then, but the multiple of this would became 0, because this vector itself became 0. Okay, because the vector itself is 0, I can put any value of the scalar and the whole set would become 0, and the whole set would be 0. Okay, that's why I have said that the value of the set of the vector which have one vector as the 0, this set of vector would be linearly dependent, because the value of that vector 0 can be assigned any of the scalar 1, 2 or any scalar. Okay, that the coefficient of this ui is not equals to 0. Let's write it down in a proper manner, because it is a very important definition. Let's say I say that 0 is that from this set u1 to un there is one vector which is u1 ui which is equals to 0, u1 which is equals to 0. Then these set of vectors must be linearly dependent, because we have linear combination where coefficient of ui is not equals to 0, as 1 u1 plus 0 u2. This is the required linear combination for which we can say that the whole sum um equals to 0. That the whole sum is making the resultant as 0, but the coefficient of this u1 is not equals to 0. That's why this set is linearly dependent. Because for linearly independence, we should have all the value of the scalar should be equals to 0. But here, the value of this scalar is not equals to 0. That's why it is linearly independent. Okay. Now let's see another important result, which is as if I have two vectors. This is another result. If I have two vectors, let's say ui and uj, and from these vectors, one can be represented in there, and another one can be represented in the scalar multiple of other. Okay, let's like this: ui equals to k of uj. Okay, where k is not equals to 0. Okay, then these vectors are linearly dependent. And these vectors are linearly dependent. How? Let's see this. Let's say we have the linear combination where ui's are not equals to 0. Okay, let's give them a value u1 equals to ku2. Okay, I have this linear combination u1 equals to ku2. Now I can define it like this: u1 minus ku2 equals to u1 minus ku2 plus 0 u3 plus 0 u4 0 un. I have this set of combination. This set of combination here. Okay, I have this set of linear combination here. Here we can see that I have assigned the value of the scalars for all these fields are 0, but you can see that the value for this scalar is -1, and the value for this vector scalar is -k. But the whole vector u1 u2 to u1 u2 to un, this linear combination is making the resultant as 0, but the value of this scalar and this scalar are not 0, so this set of vector is linearly dependent. Okay, now so when I say that the set of vector u1 u2 to um is linearly independent, then then any rearrangement of this, this is our another result, that any rearrangement of vectors, of these vectors, let's say ui1 ui2 to uim, is also linearly independent. It doesn't matter on the rearrangement of the vectors, that if the set of vector is linearly independent, then we can arrange them in any way, they will remain linearly independent. Okay, and let's say another result, if the set of vectors u1 to un is linearly independent, then any subset of these vectors also be linearly independent. And similarly, if the set of vector is linearly dependent, then any subset of these vectors will also be linearly dependent. Okay, got it? And also there is another result, you can write them down. Okay, these are some important results which will be used in the solving questions. I have a set of vectors u1 to um. Let's consider this is linearly dependent. Then the superset of this linearly dependent set of vectors in V vector space is also linearly dependent. Superset of these linearly dependent set of vectors in V vector space is linearly dependent. Okay, you better got it. Okay, now let's see it. There are some important theorems. These are the basic theorems which we have, these are the basic results actually which we have studied till now. These are the basic results. Now let's some important theorems about it. Let's see. Okay, first one would be like this: let x be a set of vectors in a vector space V. Okay, there is a x which is the set of vectors. Let x be a set of vectors in vector space V. Okay, in vector space V, and we are considering A. From this x, what is this A? This A is the set of all maximum number of linearly independent subset of x. What is this x? A which is the subset of x, which belongs to x, which is the subset of x. But this A is maximum number of linearly independent set of vectors. Okay, and if this A is finite, then, and let's consider it has size k. The number of vectors in this has size k. Then no linearly independent subset of x has a size more than k. No linearly independent subset of x has a size more than k. Okay, what did I say here? that if I have a x, if I have a set of vectors which is x, okay, from the vector space V, and from this x I have a set of vector which is the all the number of maximum number of linearly independent set of vectors from the set of x, okay, and where this is the required condition that A has to be finite. The set of vector which we are considering, the independent set, linearly independent set of vectors, maximum number of linearly independent set of vectors A has to be finite for this. Has to be finite for this. And if the size of vectors is a size k, then it is the maximum number of linearly independent set of vectors of size k. That means no linearly independent subset of x, that it does not contain any linearly independent set more than k. Linearly independent subset of x more than k. Okay, it doesn't contain that. This is the maximum number of linearly independent set of the vectors. It is a simple definition or simple observation. Okay. Now let's talk about these vectors with respect to the spans. Okay, we have studied the concept of the span, which also related to the linear combinations. And this the concept of linear dependence and linearly independence. This is also related to the linear combination. Okay, so let's study these linear dependence and independence concept with respect to the spans. How these are related. Okay, so if I have the set of vectors x1 to xk, let's say these are linearly dependent. Okay, these are linearly dependent. And from this set, I have xj vector. Xj vector. That means here xj j is actually 1 to k, belonging to this set 1 to k. It is belonging to this set of vectors. Okay. Okay. If xj belongs to the span of x1 to xj minus 1, then this set of vectors is linearly dependent. Okay, what did I say? I say that the set of this vector x1 to xk is linearly dependent if there exists vector xj from this vector which is the span of x1 to xj minus 1, which means that xj can be represented in the linear combination of x1 to xj minus 1. We can see it like this, that let's first consider that xj belongs to this span. Okay, then it means that xj can be represented in their linear combination as alpha 1 x1 to alpha j minus 1 xj minus 1. Okay, I can also represent this set of vectors to xk. It is from 1 to j minus 1 here. I'll extend it to 1 to k, which is alpha 1 x1 to alpha j minus 1 xj minus 1 j minus 1, and subtracting xj here, I get 1 minus 1 dot xj plus 0 dot xj plus 1 to 0 dot xk, which is equals to 0. So from this we got that x1 to xk are linearly dependent. As we have also said earlier, that if I put all the values of alpha j is equals to 0, then there is one vector xj which doesn't have value equals to 0. It has the value of the coefficient is minus 1. So the coefficient of alpha j is not equals to 0. Because of this, the set of vectors, whole set of vectors x1 to xk is linearly dependent. Now let's consider it the other way. If I say that the set of vectors x1 to xk is linearly dependent. Okay, I'm considering it here. Here, first I have considered that the xj belongs to the linear spans. Xj belongs to the span. Then I have proved that these set of vectors are linearly dependent, and this is the if part. If I say that x1 to xk are linearly dependent, then what does it mean? That there exist scalars alpha 1 to alpha k, not all zero, such that alpha 1 x1 to alpha k xk equals to 0. Okay, now if I talk about the, let's say we are taking the xj vector here. So if I say j equals to 1, if I'm talking about the for j equals to 1 case, then what did I get? I got the combination as alpha 1 x1 equals to 0, and because I have considered that the set of vectors is linearly dependent, then for linearly dependent I have to consider that x1 equals to 0, then it is linearly dependent. Because if I take alpha I equals to 0, then the set will become linearly independent. That's why I am taking the set of the vector x1 equals to 0. Then we can say that this set will be linearly dependent because I am considering it here. Okay, and when we talk about the j, where j is greater than equals to 2, then what will the case then? It will the case here then formed is xj equals to alpha 1 x1 to alpha j minus 1 xj minus 1. Then we can say that xj belong to span of x1 to xj minus 1. Okay, that's what we have got from here, because xj can be represented in their linear combination. So here I say this, let's write it clearly, that the set of vectors x1 to xk are linearly dependent if xj, which belong to this set of vectors x1 to xk, that if xj belongs to span of x1 to xj minus 1. Okay, this is what we have uh, studied here. This is the resultant of this all. Okay, now it can also be said in other way, a corollary of this, like a set A, which is the subset of the vector space V, is linearly dependent. This set A is linearly dependent if there exists an X which belongs to A such that X belongs to span of A except X. Okay, this is what we have gone through here, is that I have a vector xj which can be represented in the spans of others, in the span of other vectors, like this. I have represented this set of vectors in the linear combination of these except xj, because I am taking this in the linear combination. Okay, okay, now let's see another one. This is the other result which is important. If this let's say A is linearly independent. A is the set of vector which is linearly independent, and there is a y which does not belong to A. Okay, and there is a y which does not belong to A. Then A union y is linearly dependent. A union y is linearly dependent. How? The question is how. This is if A union y is linearly dependent if y belongs to the span of A. Okay, if y belongs to the span of A, then it means that it can be represented in the linear combination. And when I take the union of this, I'm talking about the whole set. And if this y can be represented in this set of linear combination, then the whole set would become linearly dependent. That's what we have done in our previous example. Okay, so if I have a set of A which is linearly independent and there is another y which does not belong to this set, and the union of this A union y would become linearly independent if if this y can be is the span of these AIs. If this y is the span of this AI. Okay, I think you got it. Okay, now there is another okay, and there is another result like this, that if A is the set of vector, I say that A is a set of vector like x1, x2, xk. Okay, and B is another set of vector which is y1, y2 to yk plus 1. And these both set are linearly independent. linearly independent. Okay, then if I define yj which belongs to this their subtraction b minus a. Okay, then I define yj which belongs to b minus a. B minus a. Then this set of vector yj with the a union yj would also become linearly independent. How? As I have said, the set of vector a here is linearly independent and the set of vector b here is also linearly independent. Then if I subtract b minus a, then the remaining vector of these are also linearly independent. And if I take the union of this linearly independent vector with a set a which is also linearly independent, then the whole set would also become linearly independent. Okay, well, got it. Okay, now let's see an example. Let's see it by an example. If I have the set S. If I have the set S as alpha to alpha beta, okay, then what is this? Whether is this set is linearly dependent or linearly independent. You can see clearly that 2 alpha belongs to the set S and it can be represented as 2 alpha equals to twice into alpha plus 0 into beta. So it is being written in the linear combinations of the remaining vectors, that 2 alpha is written in the linear combination of the vectors alpha and beta, like 2 alpha plus 0 beta, where the coefficient of the vector alpha is 2 and the coefficient of the vector beta is 0. Okay, so this set of vector is linearly dependent because there is one vector in this set which can be written in the linear combination of the other vectors. Okay. Okay, let's see another example. Okay, if I have this set of vector, let's say S, which has vector as 1 2 2 2 1 2 and 2 2 1, and I have to check whether this set of vector is linearly dependent or linearly independent. So for this, I'll just put them in the linear combination of the vectors. For the scalars Ci's, which is C1 alpha 1, I'll assign these as alpha 1, alpha 2 and alpha 3 vectors. Then the linear combination would become C1 C2 alpha 2 plus C3 alpha 3 equals to 0, which is as just putting the value of the vectors as 1 2 2 plus C2 2 1 2 plus C3 2 2 1 equals to 0 0 0. Okay, now form the equations from this, which is C1 plus 2C2 plus 2C3, which is equals to 0. 2C1 plus C2 plus 2C3 equals to 0. This is our second equation. And 2C1 plus 2C2 plus C3, which is equals to 0. Now these are the three equations which we got from here. Okay. Now we can just solve this problem as considering and transforming this into the determinant. Okay, into the matrix, actually into the matrix. Let's say, because if I solve this by solving the equations, then it would be like very complicated calculation. I'll just transform this into the matrix form as 1 2 2 2 1 2 2 2 1. So for the linearly independence, what I have to do, I have to find the value of the scalars. If these set of values of the scalars are 0, then I say that the vectors are linearly independent. If this set of vector value of the scalars are non-zero, then I say that the vector set of vectors is linearly dependent. So basically I have to find the value of C1 C2 C3. Okay, so I can solve this set of equation by the help of Cramer's rule. Okay, by the help of Cramer's rule, this would be like the simplest way of solving here is because from the Cramer's rule we all know that if I have the set of equation as a1x b1y plus c1z, which is equals to d1, and another equation a2x B2y, C2z equals to D2, and A3x plus B3y, B2y, B3y plus C3z equals to D2. Then according to the Cramer's rule, that the set of that the determinant of these A, which is A1, A2, A3, B1, B2, B3, C1, C2, C3. If the determinant of this A is not equals to 0, then we can find the solution of this x, y, z as x equals to uh, d1, d2, d3. Will replace the values of the coefficients of the x by their d1, d2, d3, b1, b2, b3, and c1, c2, c3 upon determinant of a. That's how we can get the value of the x. Similarly, for the value of the y and for the z. Okay, so firstly I have to check. So the basic condition in the Cramer's rule is if the determinant of this is not equals to 0, then we have the solution, and if the determinant of this is equals to 0, then we doesn't have the solution like this. Because let's apply the Cramer rule first, then you'll see it clearly. I'll find the determinant of these values as 1, 1 minus 4 minus 2, 2 minus 4 plus 2, 4 minus 2. From this I got 2 to 4, and it would become 5. Okay, the determinant of A is equals to 5, which is not equals to 0. Then we have the solution like this. Okay, if I find for the value of the C1, if I find the value of the C1, this is the set of the equations here is. If I find the value for this, then the determinant, which is this part, would become 0, 0, 0, 0, 0, 0, 2, 1, 2, 2, 2, 1. So as the determinant of this, as the whole row is 0 here, the whole column is 0 here, the determinant of this would become 0. And similarly for the C2, the determinant is 1, 2, 2, 0, 0, 0, 2, 2, 1. So the determinant of C2 for this also became 0. Okay, so from this we get that the value of C1, C2, C3 are all 0. So this set of vectors is linearly independent. So by Cramer's rule, we can easily check by finding the determinant whether this will contain a proper solution or not. Okay, let's see another example. Firstly, we have to erase. Okay, let's just take another sheet. Okay, let's say I have a vector space V over R, and the functions as ft, which is sine t. Okay, and gt is another function which is e's power t, and ht, which is as t square. Okay, now for this I'll form the equations. Okay, I'll form the equation for checking whether this set of functions is linearly dependent or independent. Let's form the equations as xf plus yg plus zh equals to 0. Now put the value of these functions as x sine t plus y is power t plus z t square equals to 0. Okay, this is the set of the function that I got. Now I want to check the linearly dependence and linear independence and dependence of this set of functions. For this, I have to find the value of the scalars x, y, z. Now let's check it like this. We can't just put the values of these functions as this is the polynomial, this is the exponential, and this is the trigonometric function. For this, we have to just put the values of the t. For different values of t, what would we get? Then we can find the value of the scalars. Let's say I have put the value of the t as 0. Then what will be the function become? It became x sine 0 is 0, plus y e's power 0 is 1, plus z 0's power square, which is z equals to 0, into 0, which is equals to 0. So y of 1 equals to 0, y equals to 0. And if I put the value of the t is equals to pi, what did I get? As x sine pi is 0, plus y is power pi, y is power pi plus z pi square equals to 0, and we have got the value of the y as 0, so this function will become 0. So I got z of equals to 0, z equals to 0. And if I put t equals to pi by 2, what did I get? Pi by 2, sorry, x of pi by 2 or sine pi by 2. What is sine pi by 2? It is 1 plus I have value of y and value of z as 0, so it will become 0 plus 0, which is equals to 0. So I got x equals to 0, 2. So I got x equals to y equals to z equals to 0. So these set of functions are linearly independent. Okay. Now, if I say it like this, that I have, let's say I have the two set of vectors, which is u comma v in R cube, okay, in R cube, which are linearly dependent. When can we say that the set of vectors in R cube are linearly dependent? If they lie on the same line though origin. These set of vectors will be linearly dependent if they lie on the same line though the origin. Let's like this. This is the plane here in the R cube. Then this set of vectors u and v, okay, sorry, let's form another. I can't be able to represent here in a proper manner, so my drawing is actually too bad. Okay, so this is the plane here. This is the origin part. So these set of vector, these two vectors u and v in R cube are linearly dependent if they lie on the same line the origin, like this. This is the vector u and this is the vector v. Then the set of vector a are linearly dependent. Okay, I think you got it. So these are some examples from which you can check that whether the vectors are whether the functions, vectors, whatever you want to check, is linearly independent or linearly dependent. Okay, now there is a very important concept of linear independence and linear independence in the matrix form. In the matrix, let's say I have a matrix of any m cross n. Okay, now if I want to check whether this set of whether this matrix actually uh, the elements of the matrix, let's say this, I have also said that the elements of the matrix works as a vector. This is the row vector and this is corresponding is the column vector. This is a row vector, this is a column vector. The elements of the matrix works as a vector. Okay, now we can also check whether the matrix is linearly dependent or linearly independent by also considering these elements of the matrix as vectors. And also there is another concept of rank, through which we can check whether the matrix is linearly dependent or linearly independent. Okay, we'll see it further in our further lectures. Okay, thank you. This is all about this lecture.